Hello everyone, it's Dr. Marks, and our topic for today is data and the data collection process. Now, in the last lecture, we talked a little bit about the definition of statistics, and we made some key distinctions. For example, the distinction between descriptive statistics, where we're just describing with things like mode, median, graphs that present our data and show trends and patterns, and inferential statistics, where we have some mathematical approaches to taking our subjects and then inferring about our population. So we said that this semester we're going to be covering both descriptive and inferential statistics in this class. Then we talked a little bit about sampling, which we'll talk more about here, and the concerns for selection bias, right? What happens if I have a sample that doesn't really look like my population? We noted that research can be experimental or non-experimental. Remember, I gave you the example of doing a study on the impact of drinking on student GPAs. Clearly can't do that as an experiment with a treatment because that would be highly unethical. I'm sure my university would turn down any proposal for any such type of research. Then we introduced some terminology, dependent variable, independent variables, things that we're going to need to have in our toolkit as we continue in this class. And we wrapped up by talking about ways data and statistics were used and are used in the real world and how they affect our lives. So now we're moving on to talk about the first part of the definition of statistics, and that's collecting data. Now, we're going to cover some definitions in this particular lecture that we're going to use throughout this class. So we're going to be adding to our vocabulary, and so it's going to be important that we keep kind of a running note of all of the new terms that we've added. So back to our definition. We said that statistics is the science of collecting, describing, and interpreting data. And as I said, this particular lecture, we're talking about collecting, the data collection process. Now, I know that in some of your jobs and industries where you're employed, data collection is highly important. And I know you already understand that if you're making decisions based on data, then you need to collect data very accurately. And by accurately, we mean without selection bias, as one of the very key things that we have to think about. When we talk about selection bias, we're asking ourselves, are those participating in a study or the ones for which we're collecting data on, are they different from those who were not collecting data on or who are not participating in this study? If we answer yes to that question, if these are different, well, we might have some selection bias, and that could cause us to make very bad conclusions. It's going to influence our results. It's going to have us making inferences that we shouldn't really be making. So if we want a formal definition of the idea of selection bias, a very standard definition is that selection bias is when individuals or groups in a study differ systematically from the population of interest, right? Let's say that again. Individuals or groups or whatever entities in a study differ systematically from the population of interest. And this leads us to systematic errors in an association or an outcome. We're going to make bad decisions. We're going to make bad inferences because of this selection bias. So for example, let's say that we're doing some research on the opinions about forgiving college debt, right? There's been a lot of talk amongst politicians about should we forgive college debt because college is getting super expensive and it's creating quite a burden on students. But do you agree? We're going to get different answers depending on who we ask. So it could be that your attitudes on forgiving college debt are related to income. Maybe lower income and higher income people have different views. And if that is the case, then we need to make sure we don't have selection bias where we capture information only from one income level or one range of income levels. Or maybe people who have college debt feel differently. I've certainly heard people say, oh, you know, I had college debt and I had to pay mine and other people shouldn't get a free ride. Well, I'm not saying that's my opinion, but you've heard people say that. So certainly it might be reasonable to suspect that people that have college debt or had college debt that they paid off are going to have different attitudes. If you have college debt, you might be saying, woohoo, let's do this. And if you had college debt and paid it off, you're like, wait, that's not fair. So In my data collection process, I certainly want to make sure my respondents aren't skewed in one direction or the other, having debt or having had debt and paid it off. What if you have children? You might be concerned about your children's ability to go to college, and this could influence responses as well. So you get the idea that when we're sampling about people's opinions, we have to make sure we're not introducing any selection bias. What about attitudes about receiving the COVID vaccine? Certainly we could collect information from people, but we could also introduce some selection bias. What if I only survey Republicans or I only survey Democrats? Articles seem to suggest that people's attitudes somewhat align with political party. Now, I'm not saying that's true for every single person. That would be a sweeping generalization, and please understand that I'm not making that sweeping generalization, but the data seems to suggest that there are some correlations. So if I'm going to survey people, I need to make sure that I have some balance between people who consider themselves Republicans or strong Republicans and Democrats or strong Democrats, or else I might have a biased sample. What if I only survey frontline workers? Certainly frontline workers might have a different attitude. Gosh, especially if you're in the medical profession, you might have a very strong attitude about the COVID vaccine. And that might differ from yet other frontline workers or everyone else. So I'd have to be very careful. I want to have a balance of people, frontline workers, not frontline workers. What if we're testing the effect of additional workforce training on performance? So I want to do a study. I want to see if training people in their jobs with whatever kind of training processes affects performance. So this might be something of interest within your business or within your industry. But let's say that I let people volunteer to participate. All right, is it possible that I have introduced some selection bias by asking people simply to volunteer? Well, I want to see if those who received the training have higher performance on some tasks than those who did not. So maybe there's selection bias in who volunteers. I have to be very, very careful there. If I think that it's possible that maybe higher performance people volunteer, or people that are more open to training are the ones that volunteer, and therefore it could influence performance measures, I could have some selection bias. So again, better employees tend to volunteer. I have just messed up my entire study. I'm not going to be able to claim that what I'm learning from my sample reflects the population, making inferences inaccurate. And again, if all my employees that volunteer are my weaker employees, I'm going to have the same problem. So bottom line, again, I've given you a number of examples. We need to think about this in our research design. So as we collect data, which is a very important part of the research process, we need to be thinking about whether we've introduced selection bias. Now, selection bias can enter in a lot of ways. I've just given you kind of a few examples, but one way that it clearly can enter is who is likely or unlikely to answer a survey. So even if I throw out a survey there, maybe only certain types of people would be inclined to answer a survey. So for example, I'm involved in a big project right now, and we're going to be surveying many hundreds of people. And we understand that selection bias could be an issue given our particular topic. So how have we solved this problem? We have created some quotas on things like gender, age, race. We're trying to make sure that these parameters reflect the census in terms of what our population looks like. So I can't guarantee that eliminates all selection bias, but I'm going to do my best to make sure that I have a sample that represents the United States population. Now, what about people that might abort in the middle of a survey? You know, that could be a source of selection bias too, that maybe certain kinds of people are more likely to abort in the middle of a survey. Maybe they get to a certain question and certain kinds of people are going to be maybe a little more upset about the nature of that question or the topic of that question, and they're more likely to abort. So now I've got a potential source of selection bias. who you might approach if you're surveying in person. So if you're going to do an in-person survey, you need to think about who you might physically be approaching. And this is going to depend on where you are. So let's say that my boss says, I want to go out and get information from people on the street. Great, that can be valid, but where I'm physically standing could matter. If I'm standing in front of Walmart, I might get a different class of people than if I'm standing in front of like a high-end, more expensive grocery store. So again, maybe I need to be sampling in multiple places, trying to get some kind of balance. We've already mentioned if people are volunteering to participate in a pilot, you would want to make sure that your volunteerism isn't skewed in one direction or the other. Is it that stronger employees are volunteering? Is it that lower income people might be volunteering? Again, this can introduce selection bias if you don't think your volunteers go across a spectrum that represents your population. Where your data is collected from. This could also lead to some selection bias because we have already talked a little bit about this issue with data literacy in our country, and sometimes data can be distorted. So if I'm collecting data for use in a study, I want to make sure that that data has been collected well and has been reported accurately without any kind of bias. So as I said, it's important to think about all of these types of places that you could see selection bias in your research design. And that's just really about doing good research. And this is also related to the idea of conducting ethical research, right? As researchers or analysts, you want to make sure that you are conducting your research ethically, free of bias, free of manipulation. And this would just be one element related to that. So more on this later, but I did want to introduce the idea. Now, keep in mind when we're collecting data, as we've already mentioned, we're trying to learn about a population, but we haven't defined population yet. So population is defined as a collection or set of individuals, objects, or events whose properties are to be analyzed. So a collection or set of individuals, objects, or events whose properties are to be analyzed. And notice it's not just individuals, right? Because a population can be more than just people, and we'll look at some examples in a moment. So an example might be, I'm interested in looking at something related to males under the age of 50 living in the United States. And that's a whole lot of people, right? And so this is a pretty good population. I'll need to get a subset of this. What about Longwood University MBA students? Okay, that's a smaller population. So if I look at all the students who have either graduated from the Longwood University MBA program or are currently enrolled in the Longwood University MBA program, I have a population. It's a more narrowly defined population. It's a smaller population. And do you agree it's possible I might be able to collect data on that population or pretty darn close to the entire population? Now, a population might be finite, and finite means that there are clear boundaries that distinguish this population group from other population groups. So I can say, yes, no, we can kind of draw a line. And so populations might be finite. If they're finite, then they have to be limited in size. So we've got these clear boundaries that distinguish this group from other groups, giving us a size limit. And so the examples that we've already looked at would be finite, right? If we looked at MBA students at Longwood University, that is a finite countable population. If we looked at males under 50 living in the U.S., it's a bigger population, but that is indeed a finite population. There's a clear boundary, right? I know if you're a woman, you're not in that population. If you are anybody over 51, even males, you're not in that population. If you're not in the United States, you're not in that population. So that is also a finite population. A population might also be infinite. Now, we don't use much of this in the business world, but it's still important that we understand it. So Infinite means that there are no clear boundaries that distinguish this population group from other population groups. So how is it possible that there'd be no boundaries, right? That's hard to get our brain around because we're usually thinking about businesses and there's boundaries, people, there's boundaries, but there are examples. If we have an infinite population, then it's unlimited in size. And so if it's unlimited size, then it's not possible that we can count the number of subjects in the population. So what would be examples of this? Well, if we were looking at the population of stars in space, that's probably infinite in terms of not being countable. If we're looking at red blood cells in the body, same kind of thing. It's not a quantifiable number. It's just too large. It'd be impossible to count. It's unlimited in size, but most of us probably aren't dealing with the number of stars in space or the number of red blood cells in the body. So in the business world, we likely work with finite populations. And in this class, we're going to be dealing with finite populations. So that's the good news. They are countable, but they might be very large. It might require us to have a sample from which we can make inferences. So medical research, anybody involved in that? Infinite populations might make sense. They might also have finite populations, but as we said, for us, for this class, finite populations is what we're going to be sticking to. Now, it's important to understand that an entity or a subject can be a person. So if we're talking about the number of CPAs, we want to look at CPAs, or we want to look at males under 50. Those are observations that are people, but we could also be looking at a data set about firms. And in that case, our entity is a firm or a business. Or if you're doing educational research, your entity might be a school. And so we want to get in the habit of remembering that an entity doesn't just have to be a person. So there's lots of different ways to define an entity. And so it's helpful to ask yourself when you're looking at situations or examples or data sets, what actually constitutes an observation? So when you're thinking about a study, you're working with a data set, what constitutes an observation? So let's look at some examples. What constitutes an observation in these examples? All right, number one, we have a data set on student test scores on a K through 12 standardized test. So somebody gives you this data set, you're working as a consultant, and they say, we want you to do some research for us. What constitutes an entity here? Well, seems like it would be a student, an individual student, because these are student level test scores. So in this case, an entity is a person, and it would be a student taking these K through 12 tests. But what if instead we have data on the average test scores at K-12 institutions? Well, it's similar data in the sense that it's on these standardized tests, but instead we have an average test score across institutions. Do you agree that in this case, an observation is going to be an institution, like a school? So it might be that we have a whole set of elementary, middle, and high schools, and we have their averages. Please understand, with this example, an entity is no longer an individual student. Third, let's say we have percent of smokers by state, and we're doing some kind of analysis based on this. So what constitutes an entity here? An observation is, it's not a smoker. Everyone agree it's a state because we have percent of smokers by state. If I look at the data, a row of data is going to be a state. So it might say, Virginia has this percent of its population that smokes. North Carolina has this percentage of its population that smokes. So the entity is a state. Sales prices for houses listed in the MLS system. Well, in this case, an entity or an observation in your data set is going to be a house. So you're going to have data on individual houses and those sale prices. So a row of data in your spreadsheet would be a house. Average home prices per county in North Carolina. So maybe you're doing some consulting for the Real Estate Association in North Carolina, and they give you a data set that has average home prices per county in North Carolina. So what is an entity here? it would be a county, because what kind of data do you have? Average home prices, but you have it at the county level. So I don't know how many counties are in North Carolina, but let's say there's 50. We would have 50 lines of data. Each row of that data would be a county with an average home price. Life expectancy by country. Clearly in this example, an entity or an observation would be a country. So what's the life expectancy in Thailand? What's the life expectancy in Malaysia? What's the life expectancy in Vietnam, etc.? Number of employees for businesses in Virginia. If you have a data set on number of employees for businesses in Virginia, your entity is a business in Virginia, of course. And finally, lead admission levels for California vehicles. This might be a data set on individual vehicles. All right, you guys get the idea. Bottom line, what I'm trying to communicate to you is that sometimes we're going to have data sets that we work with that are individuals, but sometimes they could be schools, they could be states, they could be counties, they could be countries, they could be businesses. So get in the habit of thinking, what is an observation in the data set I'm working with? As we've already mentioned, the goal of data collection is generally to learn about a population. It's usually a population that's of interest. And to do this, we have to collect data on a sample. So generally, a sample is going to be a subset of a population. And I say generally because there could be an exception to this. But generally, a sample is going to be a subset of our population. And why? Again, because it's not always feasible to collect information on an entire population, especially if we're talking about all males under 50 residing in the United States. So keep in mind that even if a population is finite, like all men under 50 living in the USA, that is a finite population, right? It's not infinite, but it's still probably prohibitively large. So again, we have a population. Let's say we want to collect the IQ of all college students in the United States. Well, all college students in the United States, that's a huge number. There's no way we're going to be able to get every single college student. So instead, as it shows on the right, we're taking this smaller sample. Again, we've talked about selection bias. We need this to be a representative sample. So maybe I find the IQs of 2,000 randomly selected college students. Again, why randomly selected? That's going to avoid the selection bias problem that we've already talked about. Now, in some contexts, a population and sample could be the same. And so I don't want to confuse anyone here, but this could be the case when research is limited to a specific group, when it's really just a small group you're trying to learn about. And in that case, it could be feasible to get data on all of your subjects. For example, I was involved in a consulting project for a rural school system, and they were taking these standardized tests, our standards of learning tests, we call them in Virginia. Now, it was a pretty small school, and I wanted to help them learn what was driving their test scores. So my population of interest was their students. And I need to think about, does race, if students are economically disadvantaged, if they have excessive absences, do those types of things drive test scores? Now, the population of interest was students at that particular school. I wasn't interested in every single student across the United States because I was working with just this rural school system. And I was given data on all students at that school. So because I was interested only in students at that school, since I was consulting for this school system, and I was given data on all the students at that school, then do you agree I have a population that's basically equal to my sample? Now, maybe there was somebody missing. I don't believe there was, though. So literally, I could argue that my sample was the population of interest. But that's only because I was consulting for this particular school, and the population that I was interested in, the SOL test scores for students in just that school system. But here's the thing. What if I'm using this school's data set with their students in order to learn what affects test scores in general for the same age group. And in general, I mean, across the United States. Now, here's where I'm going to start to have a little trouble. Can I say that I have the whole population? No. I just have, in this case, if I want to learn about the whole United States, I have a sample which might have some selection bias. So I'm working with a sample, students at this rural school system in Virginia, and I want to learn about the population, students in general, in the United States. You see the problem now, I do have a population of interest, and I have a sample just from that school system. So we're back to our sample being a subset of the population. But I also have to think about how well the sample is going to teach me about the population. When I had, 3,000 students, that's data across many years, and I want to learn just about that school system, that's fine. But if I have data from this rural school system and I want to learn about the population, where I'm now defining the population as school-aged kids across the United States, that could be a problem. And I have to ask myself again, is there selection bias if I'm using the results from this one small school to learn about the entire population? And so somebody could argue, hey, wait a minute, this might not be a representative sample because it's not a random draw of subjects from the population, because this was a school that was highly rural and incomes were on the lower end, and there was a different composition of minorities, for example. So we'd have to ask ourselves, are they distinctly different from those not in the sample? Yeah, they might be, because they're all in a rural area of Virginia. So that might not have been a good sample if I wanted to learn about the entire population. But it was a good sample if I just want to learn about this rural school system. I hope that makes sense. So getting back to this idea of data collection, we usually want to create a data set for our sample in order to learn about the population. And this is going to be comprised of variables. So we already understand we use data on our sample to learn about the population, but now we're introducing the idea of variables. So we're going to have variables. So what's a variable? A variable is a characteristic about each individual entity or subject of a population or sample. So a variable, characteristics about each individual entity or subject of a population or sample. So there's a lot of words in there that we understand. We understand population, we understand sample, and so our data set is going to be comprised of variables. So what might be variables of interest? Well, depending on our study, age, height, weight, experience, salary, race, gender, these are all variables. And so clearly I need the ones that would be relevant for my particular study. Now we can divide the idea of variables further by understanding that variables can be either quantitative or qualitative. So quantitative variables are going to be those variables that quantify an element of the population. So if a variable quantifies something, right, it's going to be something numerical, a quantity, then it's a quantitative variable. But we also have qualitative variables, and qualitative variables categorize or describe an element of a population. So quantitative variables quantify with like some kind of number, and qualitative variables categorize or describe. So what might be some examples? Well, variables that quantify: age, years of experience, salary. Do we agree that those are all quantitative variables? Where qualitative variables that categorize or describes might include gender, it's a description; race, it's a description. Do you have a college diploma? That's a yes/no question. It's not a quantification. So that would also be a description. So quantitative versus qualitative variables. So as we just said, we can start with our variables and divide them into qualitative and quantitative variables. However, we can refine this even further. data can be broken down with subcategories for both qualitative and quantitative. So we're going to add on to this chart. If we're looking at quantitative data, it can be either discrete or continuous. Now remember, quantitative data is numerical, and so we're talking about numerical data that is discrete or continuous. If we have a discrete variable, then that's going to be a variable that takes on only certain measures. It's going to be a countable number of values. So discrete, it takes on only certain measures, countable numbers of values. So think about discrete variables as having space between the units, right? You can kind of draw a division between the units. There's space between the units. For example, number of years of high school that have been fully completed. Well, it says fully completed. So the answers are 0, 1, 2, 3, 4. And I guess 5 if you stayed extra, but we're saying out of the academic year. Doesn't matter. So do you agree that there are spaces between the units? There's not partial units, in other words. So it's either 0, 1, 2, 3, 4. Or we might be asking you for the number of dependents in your household, and you don't have a fraction of a dependent. I don't have half a child or 3/4 of a child, so I have dependents. Either have no dependents outside of myself, 1, 2, 3, 4, 5, so on. You get the idea. We could be looking at the number of employees retiring from your firm this year, and again, that's going to be a discrete number. It's going to be 1, 2, 50, 80, 27. These are discrete numbers because there's no fractional units, right? That's kind of the key with discrete data. There's no fractional units in this sense. And if there were, there'd still be space. I could probably come up with a discrete example with fractional units, but I don't think we'll be employing any of those for this class. So what we're basically trying to say is quantitative data that is discrete means we don't have a continuum of possible values. So then that brings us to continuous data. If we have variables that are continuous, then those variables can take on an uncountable number of values. Where before there was just a specific number of values, now there's an uncountable number of values. So it could be any value along a line interval from X to Y. It could fall anywhere in between. For example, weight. That is actually a continuous variable. We tend to round and express weight as if it's discrete, 125, 126, 127, but the reality is that weight is a continuous variable because there are fractions of ounces and fractions of pounds, and really it can be anything from, it could be from 0 to 500 depending on what we're talking about, and it could be anywhere in between. Distance is another example of a continuous variable because it can be measured in feet, it can be inches, there are fractions of miles, fractions of kilometers. It can take on any value in a range of values. Work experience is the same way. Now, if we were saying total number of years of work experience, that's different. But if we just say work experience, technically this can be, up to the day, it can be up to the hour, it can be up to the minute. It's technically a continuous variable. But do you agree that we sometimes express these as if they are discrete, but they are indeed continuous? So now back to our little flow chart so we can understand and kind of visualize this. I'm all about visualizing, don't memorize. So we have variables that can either be qualitative or quantitative. And if we have a quantitative variable on the right-hand side of this diagram, quantitative are numerical measures, and they can be discrete, like 1 year, 2 year, 3 year, 4 years, and total number of years of college, or it could be continuous because we have data that falls along a spectrum, distance, for example. All right, So now let's go to the left side of this diagram and look at qualitative data. So we're done with quantitative data. Qualitative data can be broken down into ordinal or nominal measures. So qualitative data is either ordinal or nominal. Ordinal data are variables that are qualitative, but they have an ordered position or rank. So ordinal means like ordering. So variables that are qualitative, but they have an ordered position or rank. For example, you might be asked to indicate the highest degree you've earned, and your choices are high school, bachelor's, master's, or MBA, they're lumped together, or PhD. All right, well, do we agree that there's an ordering there? We all agree that bachelor's is more education than high school, a master's or an MBA is more education than a bachelor's, and a PhD is more education than a master's. So there's a natural ordering there, making this an ordinal variable. Or we could look at the grade earned in this class, and the typical grading system is A, B, C, D, F. Now, hopefully we're all in the A and B range, but with my undergraduate classes, I'm definitely going to have some that fall into the C, D, or F range, depending. And so, do we agree that those are ordinal variables? Every student knows an A is better than B, and a B is better than C, and a C is better than D, etc. Now, another thing might be a Likert scale on a survey. And if you don't know what I mean by Likert scale, we're just talking about an ordinal scale like rate 1 through 5, your level of satisfaction with. So maybe at the end of the semester, you're going to get a survey saying, rate your level of satisfaction with Dr. Marks' lectures, rate your level of satisfaction with your interaction with Dr. Marks, etc. Those are Likert scales. And do we agree that depending on how it's defined, 5 might be defined as better than 4, where 4 is better than 3, and 3 is better than 2. So Likert scale is also ordinal. What about class rank? So we graduate from high school and somebody's ranked number 1 and somebody's ranked number 2 and somebody's ranked number 3. Those are ordinal measures as well. Or maybe your company has a sales competition and they rank the winners 1, 2, and 3. Again, it's ordinal data. But we need to ask ourselves, why are those last 3 examples ordinal? Because they were numerical as well, right? We had class rank 1, 2, 3. We had rank in sales competition 1, 2, 3. We had Likert scales where you had to rate on a scale of 1, 2, 3, 4, 5. So what makes these ordinal? Because they are quantified, right? They're numerical. So why are they not in the other category? Why are they ordinal? Well, the reason is that these numbers themselves don't have any interpretation in magnitude, right? What's 1 versus 2? The ordering makes sense to me, but outside of the ordering, I don't know what a 1 is versus a 2. It doesn't really tell me anything. So we can only order this. We can't make any other sense out of it. There's no meaning otherwise to the numbers. For example, if your rank is number 1 in the sales competition, that doesn't necessarily mean you had double the sales of the rank 2 person, or the rank 2 person didn't have necessarily half the sales. I can't infer anything from that other than the person who got the rank of 1 sold more than the person who got the rank of 2. And same thing if we're talking about class rank. The salutatorian has a higher GPA than, the salutatorian does not have a higher GPA than the valedictorian, but we can't say they have half the GPA. We can't even say that each pairing has the same difference in proportion of GPAs, right? I mean, there's nothing we can conclude there. If I look at a whole ton of pairings of valedictorians and salutatorians, all I can tell you from that is the valedictorian has a higher GPA than the salutatorian. They could be like 0.0001 apart at one school, and they could be 0.05 apart in another school. There's no interpretation related to magnitude that I can glean from that. All right, you probably understood all that. So now that we understand ordinal data, let's talk about nominal data. So nominal data are variables that are qualitative but unordered. It's not a ranking. So this is the part that's maybe a little harder to understand. So gender would be an example of a nominal variable. There's no ordering, right? Male versus female. I can't say males are better than females or females are better than males. There's no natural order to males and females, right? But it is indeed qualitative. Sales regions. Maybe you're in charge of data on sales for the different regions for your business, and I've got nominal data that tells me like you're in the Northeast, someone else is in the Southwest, but there's no ordering between the different regions. We're not necessarily saying that one region is better or different than another. We're just using it categorically. Zip code would be another way. I can categorize customers by zip code, but I can't necessarily say one zip code is better than another zip code. It just doesn't have any meaning in and of itself. Political party affiliation, same kind of way. It helps me organize and sort people for my investigation, but I can't say that there's any ranking involved there. All right, so back to our diagram, because I know this was a lot. Let's look at it one more time. Variables can be divided into qualitative and quantitative variables. So remember, qualitative are those things that are used to describe and categorize people. Quantitative is numerical. Now, quantitative data on the right is either discrete or continuous, right? I've got numbers, and those numbers are either countable or they fall in a continuous spectrum. And then on the left, my qualitative data is either nominal, it's used to divide, but it's not rankable, or it's ordinal, where it's still descriptive, but I can rank. People who have bachelor's degrees have more education than people that have only high school degrees. So this is important for you to understand and get your brain around, and these are all definitions that we need to be able to work with. Now, continuing on, let's dive a little bit deeper into qualitative data, because we're going to be doing some coding with qualitative data, and qualitative data is often coded in a manner that is binary, and that means with a 0 or a 1. Now remember, guys, qualitative data is just used to categorize people, so I can use the 0-1 code for categories. So a binary variable is a variable that takes on only two states. Think of it as true and untrue. So a binary variable is either true or it's not true. It's only got two states of the world. So married is an example of a binary variable. People are either married or they are not married. So there's only two states technically, right? So it's either a yes or no question, right? If you're separated, you're still legally married, okay? So we've got a binary variable, but here's the deal. In my data set, if I have married, yes, no, the computer can't read that. Now that might be how I asked the question on a survey. So I'm working with this huge survey right now, and we do ask about marital status, and so when we capture that, it's going to be coded as, married, yes, no. But the computer can't do anything with yes, no, and so we have to convert this to something that the computer can read, and that's where the 0 or the 1 comes in. So I'm going to take my binary variable and convert it to this numerical 0-1 binary output. And in this case, it'd be very easy. 1 equals married, 0 otherwise. So 1 basically is our true state of the world. Are you married? Yes. Okay, you get a 1. Are you married? No. All right, you get a 0. And so we call this a dummy variable. So the idea of taking this qualitative data, converting it into zeros and ones, that's called a dummy variable. So when we get to week 6 or so, we're going to be talking about regression analysis. We're going to be working with dummy variables, and so we need to definitely understand that concept. You'll have some places that it's going to creep up before then, so we need to understand this. So let's look at just a very simple data set. We've got 5 employees. Some are married, some are not married. Do you see on the right-hand side, we've created this variable. It's redundant in that it's married. They're both called married, but I've converted it to a dummy variable. So Susan Smith is married. Yes, she gets a 1. And Bob Berger is not married. He gets a 0. David Davis is not married. He gets a 0. But Edward Evans and Anna Atkins, they're both married. They get 1s. So this is an example of a dummy variable. Now, here's the thing we need to understand is that we have 2 states of the world, right? Married yes or married no, but it only takes us 1 variable to capture that information here. So we don't need to create a variable called married and a variable called unmarried. That would be very redundant. I don't need to do that. I just need 1 variable. Now, what if we're talking about something that's descriptive but has multiple categories? Because that's also common. Like year in college. If I'm asking students to indicate on a survey their year in college, then I'm probably going to ask them to check the box. Are you a freshman? Are you a sophomore? Are you a junior? Or are you a senior? And again, in my spreadsheet, it's going to say freshman, sophomore, junior, senior, but that data is also not readable. So I'm going to handle this in the same kind of manner using this true or false state of the world using 0s and 1s. But because I have a bunch of different categories, we refer to this as a categorical dummy variable. So year in college, because it's not just yes, no with just 2 outcomes, is still dummy variables, but it's a categorical dummy variable. I need more than 1 variable to capture this, however. I can't simply say year in college, yes, no. So it's going to take me a little bit more work to code this than it would simply the variable about are you married or not. So I'm going to have a variable called freshman equals 1, otherwise it's 0. Sophomore equals 1, otherwise 0. Junior equals 1, otherwise 0. And senior equals 1, otherwise 0. Now, for those of you that have had econometrics, I know you're thinking, wait a minute, do you need all those? The answer is no, but just give me a second to explain it to people who are not familiar with this. So let's just start here with our 4 categories. Freshman equals 1, sophomore equals 1, junior equals 1, senior equals 1. So we've got our data set of how many students? 8 students, and I've got their years in college. But as we said, the computer can't really do much with senior, freshman, junior, senior, sophomore, depending on what it is I want to do. So let's create these 4 categories and use our 0 and 1s. So Shauna Smith is a senior. So for freshman, she's not a freshman. It gets a 0. She's not a sophomore. It gets a 0. She's not a junior. It gets a 0. She is a senior. I put a 1. So take a look really quick. Beverly Berger, do you agree with that coding? She's a freshman. Everything else is 0. Dean Davis is a junior, so it's 0, 0, 1, 0. Take a quick moment. Make sure you understand what I'm doing here. And then we can fill in the rest of the table. Boom, like that. Okay. So we've now coded our categorical variables. But here's the thing. And this is what I was hinting at a moment ago when I said, hey, those of you that know econometrics know where I'm going here, and you're probably saying, Dr. Marks, why 4 categories? We have 4 states of the world, freshman, sophomore, junior, senior, but we really only need 3 variables to capture this. It does not take 4 variables to capture this, and let me show you why. Let's say I decide to delete the category freshman. Let's just get rid of it altogether. And you might be thinking, well, then how will I know who is a freshman? We'll know. Give me a second and you'll see. All right. So I've deleted that column called freshman. So if I delete that column, how does the computer know that somebody's a freshman? Well, let's look at Beverly Berger, who's a freshman. How can the computer determine that Beverly Berger is a freshman? Because she's got 0, 0, 0. So do you understand where I'm going with this? I don't really need a column called freshman to indicate that Beverly Berger is a freshman. And in fact, this is actually the way that we need to do it. With only 3 categories coded, when there are 4 actual coded categories, 4 options. In other words, we have 1 less category than we need because 0, 0, 0 defines the 4th category. Now, do we need to create dummy variables? Well, it depends on what we're doing. It depends on the application. For example, if all I want to do is create a pie chart, do I need these zeros and ones? Not necessarily. If I have a small data set, I might be able to just do things by hand too. If I want to sort and average GPAs and all I care about is average GPA, not necessarily. I could even sort by freshman, sophomore, junior, and senior and still calculate GPAs. But for some things, like the final bullet says to run a regression where I'm controlling for year, yeah, I'm going to have dummy variables in this way. So we'll come back to this and we will be using this idea of dummy variables and categorical dummy variables this semester. So please make sure you understand it. So finally, let's just quickly recap. We've discussed the idea of data collection, and I've said it a million times. I'm sure you're sick of hearing it, but we understand that we use samples to learn about our population. But in our sampling and data collection process, we want to avoid sources of selection bias. And at this point, you should be able to describe to me things that might lead to selection bias. We've made some distinctions. We've talked about variables, and now we understand qualitative versus quantitative, and we can identify examples of qualitative data and quantitative data. But we also understand that there are subcategories, right? Discrete and continuous are subcategories for quantitative data. Nominal and ordinal are subcategories for qualitative data, and you need to be able to give me examples of those as well. So we can identify all of these things, and we've added a whole lot of new things to our vocabulary. And finally, we understand the idea of dummy and categorical dummies, something that we'll definitely be using this semester in this class. So we've covered a lot in this one particular unit. So thanks for viewing, guys. If you have any questions, please let me know. Otherwise, I hope you have a fantastic day.